whole thing. Okay, so I am recording now. As I was saying, this subject is a little bit complicated because it has many different parts, and there is a lot of material for every part, and all the parts are interconnected. You can follow a little bit about how to organize these parts I'm mentioning if you look at project number 3, for example. So let me put it somewhere here, and let me share my screen momentarily. So this one. Okay, so now you should be able to see the screen. Let me make the font a little bit bigger just in case. Okay, I can't. This is as big as it goes. Okay, so we want to speak about how to use deep learning for practical applications, okay? First of all, we're going to have to deal with the data. So what is our goal? And we need to define our problem properly. How our data can be expressed in a mathematical way, and how we can communicate with a deep learning network to solve the practical problem expressed in that mathematical way. To do that, the first thing that we have to do is organize our data somehow. For example, for the general project, or the, let's say, original version, this means having all of those mosaics, the species masks, which are all put together into the label image and the treetops. And from that information, which is a little bit overwhelming sometimes, the RGB images in the mosaic, the label images that gives us the information of what trees are in every pixel, what tree species is in every pixel, what tree species every pixel belongs to, and then the last file, the treetop mask, which tells me where every tree is. Okay, so I want to combine that to build some sort of image database that I can use. Okay, that will be what will be done in task 1. So in task 1, what you're asked to do is to create patches from the trees in one side. So I will be speaking a little bit more about this later, but basically, the first formalization that we do is that we are going to do image classification. So what we will be feeding to a deep learning network will be a set of images. And for each image, we want to get just one answer, just one code as an answer. For example, this specific patch belongs to species number 1. This one belongs to species number 2. So for every image that we build, we will want just one code, one answer, one class is called in proper terminology. Okay. So when we build our data, we want to build those images, each representing one tree, and couple them together with the correct answer. This tree is of species 1, this tree is of species 2, 3, 4. Then we will pass on this information, but our problem will be an image classification problem. Our data will be images. In this case, each image will represent a tree. And our target, what we want to get, will be just single numbers representing the codes of classes. 1, 2, 3, 4, 5, up to 44. Okay, 47, I don't remember. As many classes as we have, okay? One code for each class. So in task 1, what you will be doing will be taking those mosaics, files with treetops, the label image, so on and so forth, and building patches and storing in some way the class they belong to. The first thing that we need to do always in any deep learning project is to prepare our data. Say, for example, that instead of wanting to classify a small image corresponding to every tree, you wanted to do semantic segmentation here. What is a semantic segmentation problem? We will see a little bit more about it later. But basically, I will have larger images. Our patches will be very small, so I will have images that are a little bit bigger than our patches, maybe 500 times 500 pixels or 1000 times 1000. And I will want to know for every pixel what is in that pixel, what tree species is in that pixel, or if there are no tree species, I will give it a 0 value, saying that that's the background. There is nothing there. Okay, so when I prepare my data for the semantic segmentation project, for a semantic segmentation type of network, what I will do will be take my full data, for example, all of my mosaics, and first of all, cutting them into those tiles, 1000 times 1000, 500 times 1000 tiles. That will be my data. What will be my target? What will be my correct solution? The thing that I have to feed into the network to be able to train it. They will be tiles of the same size, and for every pixel I will have a code. Okay? 0 for background, and 1, 2, 3, 4, up to 40 something for the tree species codes. Okay? In the image classification example, my data would be small patches, 50 times 50, 100 times 100, each representing the area around the tree top. And my answer for every patch would be just one code saying what tree species is represented in that patch. In the semantic segmentation problem, I will have slightly larger images, larger tiles, 500 times 500, 1000 times 1000. And for those, my target, my correct answer to give to the deep learning network to train it will be another image. And that other image will have the code for each class at each pixel recorded, okay? So I will have lots and lots and lots of codes, one for each pixel, okay? If I wanted to do regression using deep learning networks, what could I do? Let's say I wanted to predict the amount of weed that will come from one particular plot in one particular wheat field. That's a project that we are trying to achieve with Mongolian researchers now. Then my images, my data would be the images of each one of the plots. And the correct answer would be the amount of wheat that is in every plot, a number. Okay. Simple way to, let's say, because in order to be able to solve these regression problems, I have to modify deep learning classifier networks. Modify networks such as the Resonant 50 network that you have on the notebooks, on the course notebooks, okay? One thing that can be done for this regression type of problems is to first do an intermediate step. For example, with the Mongolian professors, what we did was first see how much wheat was collected from each plot. And then we grouped them into low yield, medium yield, high yield. We did grouping 3 classes, 5 classes, okay? And then you can do an image classification problem with that much more easily without having to touch the deep learning network, okay? So to start one of these regression problems, I would suggest taking my images from the wheat, or maybe you have some synthetically generated images having pixels of different colors, and then I would count how many pixels of the color of interest are in that particular patch, in that particular image, and that would be the target. If you want to do some testing before having to modify the networks and so on, after having seen all of the contents of the different patches, you can make classes, and instead of your target being the specific number, it can be again a code, like 1 for few pixels of that particular color interest, medium or large. Or you can do as many classes as you want. Okay. In any case, the first task is always going to be preparing and manipulating our data so then we can feed it to a deep learning network. Okay. Second task, and I will stop much less at this one, will be building a PyTorch dataset. Today I will be mentioning a few things, but now I will just say that PyTorch dataset are the way we communicate with deep learning networks. Okay? And we have to follow what is called an interface. Basically, we need to define three things. We need to define the creator function for our dataset class. We need to define something called the get item. When I ask my data set for a new piece of data, what will that mean? For the general problem, that will mean giving one patch and one code. The image with the one tree represented in it and what code it belongs to. If we are going with the semantic segmentation problem, giving one piece of data, the output of the get item method would be one tile and the ground truth, all the other image with all the pixel codes, all the class codes in every pixel. If this was the regression problem, get item would output one image of one area with pixels of different colors and either the number of pixels, the specific number of pixels that are of that color, or the category if we have grouped them into categories. But I need these two things, a creator method to organize, to see how I'm going to read the data, and a get item method to give back specific pieces of data with an index that I'm provided, that I receive. Okay. The third thing is that I need to be able to say how long my data set is, but that one is pretty easy. So the parts of any deep learning network project, first one, I organize the data for myself, decide what problem I'm going to be using, and formalize things and clean them up in order to be able to feed them to a data set, which is the second step. PyTorch datasets are how PyTorch communicate with users. In task 3, we are going to be training networks, and we are going to be speaking about this a little bit next week and in 2 weeks' time. Okay. And then we go for the testing and the using and checking differences between different data sets, how things do in validation and in training, validation, and in testing. And we will speak a little bit about those today. But those are the main parts. First, organizing the data so that I know where I have everything, what my problem is in terms of deep learning formal problems. Task 2, create a data set so I can give that to a library, for example, the PyTorch library. And then task 3, define a network, train it. That's, as you will see, complicated. It has many, many steps, but usually that's a part that someone has done for us. So we will be working the most in task 1 and 2. Okay, and then we have the whole testing and going a little bit deeper and so on. Okay, so let me take one step back at this moment and go back to the history and these kind of things. Because I want to, okay, 1 second. Yeah, here I am. I want to situate a little bit where this deep learning thing is at all, and the things it can do and the things it cannot do so well. Second. Okay. Some technical problems there. I basically needed a watch. Okay, of course I have one in my screen that I didn't see. Okay, anyway. things that deep learning can do and cannot do, and how do we do them. Okay, so I have been mentioning some of them a little bit, but I will go over them in general. Last week, we already saw a little bit about this ImageNet competition in 2015, 16, where deep learning networks managed to go beyond human capacities in a problem that before had been considered quite difficult for artificial intelligence algorithms. This one is a competition where there were lots of classes to classify, so they were solving the same problem that the general formulation of project number 3 is solving. And 2015, the ResNet network managed to go beyond human capacities. Okay, that's the one that we will be using in the general formulation of the project at first. Then task 5, you can use others. Okay. So that was the beginning of a series of milestones in deep learning. Artificial intelligence, as we saw last week, had existed for quite a long time and was in a bit of a disappointing moment. But since then, artificial intelligence started gaining steam again. For example, in 2016, we had the whole issue of AlphaGo. Go is a game, Ego in Japan, usually known. That's also one of these strategy games, and you have to capture the territory indicated by either your pieces, which can either be white or black, and then you play against an opponent, and the one who ends up controlling most of the territory without getting their groups of pieces killed. So they have to have at least 2 degrees of freedom, because otherwise the opponent can just capture them. Please do not take my explanation for granted. Go and check how Ego works. It's a really nice and interesting game and super strategic. But the main point is that's very wide. It has many, many more possibilities than chess, for example. It's very simple to learn the rules to, very difficult to get to play at a super high level. And it was a very challenging problem for computers until 2016, when a deep learning based model by Google's DeepMind managed to beat Lee Sedol, which was at the moment and probably still is one of the top players in the world. Okay. This is in the AlphaGo documentary, which you can find online, and here is a link. And usually in these classes, I spend quite a lot of time with it. I don't have that time. You have the video with the longer explanation on the page of the courses, and I heartily recommend that you have a look at this documentary. It's a Hollywood type of documentary, so it's not super scientific and not super rigorous, but it does do a good job of capturing the atmosphere and the surprise, and you will see the expectation around how this whole contest unfolded, and some questions about whether or not this AlphaGo was being creative or was playing like a human being or not playing like a human being, and so on and so forth. Okay, so really interesting documentary. Some claims of creativity there, which I would probably dispute, but nevertheless a very, very interesting window onto how alpha worked, and also about the attitude that we have when we encounter we encounter a new thing that we don't fully understand. Okay, so 2016, deep learning could not only do image classification better than humans, but it could solve some pretty difficult games like AlphaGo. AlphaGo worked a little bit like we saw last week with Deep Blue, but so it did have a tree searching algorithm which had a random part, But the most important thing was that the evaluation function, the way this AlphaGo network decided whether one particular configuration of the board favored the white player or the black player, that was learned. That was not the product of a team of scientists toiling and making up rules for months, but that was something that was automatically learned. Okay. Okay. Why did that happen at that moment? Why these huge and seemingly sudden steps in development? Well, I'm going to be following a way to describe it from Jeremy Howard, a guy professor from the University of San Francisco, author of the Fast AI course, which I heartily recommend. Okay, and he answers this question by referring to a confluence of factors, at least three factors. Number one, neural networks. This type of structure where scientists try to have lots of interconnected nodes, somehow inspired by the way they see the human brain working. Okay, those are surprisingly perhaps not new. Those are almost as old as computers. 1956 is one of the first computers, Mark I, and that already had lots of hardware circuits creating a perceptron, which is one of the initial forms of a neural network. Okay, not deep learning at that moment. It only had one layer. So we have had neural networks, this idea of replicating the way the human brain works. That's probably a little bit misleading. Probably what we should say is that these neural networks, what they are, is a flexible type of function, flexible type of network that allows different connections of different types, and that allows us to model very different things. Okay, so I think the keyword here is not brain, but flexibility. So having this type of functions, this type of models that can be adapted to many, many different things. That was something that had been there for quite a long time. Okay, this flexibility is sometimes expressed with this universal approximation theorem. So these networks are wide and have many, many nodes with many, many different connections, and those can be used in theory, following the universal approximation theorem, to model anything. Okay, that sounds very impressive and maybe is from a theoretical standpoint, but that doesn't mean that they are magic or anything. So they just mean that this type of models, this type of function are very adaptable. They are very flexible. Does that mean that I will be able to solve any problem at any time? No. In order to solve problems using this type of neural networks, you have to define the proper architecture, the proper shape of the network, and then train the network. Adjust all of its parameters, which, because the network is very flexible and has lots of connections, will be many, many, many parameters, so that the network does exactly what you want it to do. Okay? So for example, if you feed it lots of patches of trees, which can either be healthy, sick, or dead, and then you train that properly and adjust the parameters of the network properly, then you can get the sick tree or healthy tree or dead tree answer class that you want. This would be, again, an image classification problem, okay? But if we don't have enough data, or the data is not representative enough, the data that I'm using to adjust the network is not really the same as the data that I'm going to be using it in my application. For example, in my training data, there are too few sick trees or too many sick trees. Then when I try to use it in a practical application, the results will not be good. All of this has statistical properties. So if I use a type of data of training data to adjust the parameters of my network that has too many sick trees, then when I try to use my trained network with real data, I will predict trees to be sick too often. If I use a set of training data that has too few sick trees, then I will miss trees that are sick in my practical application, okay? So the universal approximation theorem means that these networks are very flexible, and I have enough data and the data is representative enough, then I can use them to model any problem, okay? Any problem would have lots of small fine print attached to it, which we will speak a little bit about later, okay? The second big thing that came together is convolutions, a way to process networks that doesn't process full images at the same time, okay? That was something that had also been there for quite a long time, since 1998. So already 17 years in 2015, okay? This means that the nodes in my network, the operations that I do in here, they are usually not, they affect the whole image, but the number of parameters in each node is not the same as the number of pixels in my input image. So these nodes are somehow smaller, and when I apply them to an image, what I do is that I make small filters, they are called, and I slide them over my image and I apply them in the small regions of my image. Those are called convolutional neural networks. And again, please go to the longer explanation of this video that you have in the index if you want to know exactly how convolutional filters work. But basically, they are smaller nodes with fewer parameters that I apply by moving them over the image. So that made it possible to have networks that are less heavy in each of their nodes. Before them, at each node, what I had was something that had as many parameters as my input data, okay, which is called fully connected layers. So I do not want to have that. I want to have something that's smaller, that allows me to process the images by this sliding thing, and that makes my whole network lighter and allows me to have more nodes and organize them into more layers. And that's where the deep in deep learning comes from. By using convolutional filters, I have nodes that are a little bit less heavy, and then I can use them I can make networks with more layers, with more nodes organized in layers. Third big part of the, let's say, revolution in deep learning comes from GPUs, from hardware. GPUs, which many people use for gaming, have been increasingly used to do many simple calculations in parallel. We have been seeing in the first two projects a little bit about how to use, I don't know, list comprehensions and maps and these kind of things to process code in parallel in our CPUs, central processing units. The GPU cards, or graphic processing units, do parallel computations that are way less general. We could not fit the code we have been doing for maps and so on to a GPU, okay? But they can do the type of calculations that are needed to optimize deep learning networks, which are basically things like adding up matrices, multiplying matrices, okay? They can do those, which are simple. They are essentially matrix multiplication, for example, is just multiplying numbers and adding them and or sorting them out correctly. So they then can do those kind of very atomic and very simple computations in parallel extremely quickly, much more quickly than the CPU, no matter how many processors you have. These GPU graphic boards have very, very high number of cores, of nuclei, of small processors that can only do those very simple computations, and that's all we need to do, okay? I said there are three main things. Thing number 4 is data in this deep learning revolution, okay? Because suddenly we had deep learning networks that could be deeper thanks to computation, and we could compute more of them because of having GPUs. Then, as the ImageNet competition showed, suddenly these artificial intelligence networks were working much better than before because of the increased capacity for computation given by the convolutions and the GPUs. But the fourth, and the thing that made it really popular, is the availability of data. Deep learning could do from 2015, and we are still there, suddenly many more things that it could do, the things that it already was doing much, much better, okay? Those infinitely adaptable functions now work much easier. We started needing less and less data in order to get significantly good results, and that started most of it in terms of research in the area of medical imaging. That's where many of the deep learning networks that are being used today were developed, but quickly expanded to many other areas of research. Initially, mostly image-based research, but nowadays also, for example, text is another big area of development, okay? And processing of other sources of data, like, for example, LiDAR, which is not exactly images, okay? Some of the things that already existed, for example, reinforcement learning or transfer learning, with deep learning suddenly became much more easy to use. And I'm going to skip through those, but let me just give you an overview. In reinforcement learning, this is a little bit niche, but if we have a problem where the rules are clearly defined, we can try to get deep learning networks to improve themselves. Classical example of this is games. In games, you have some rules, and you can get, for example, a deep learning network to play against itself and try to improve, and that's called reinforcement learning. This has not only been applied to games. There are some mind-boggling applications to quantum computing, for example, for this. But this is something that had been defined for quite a long time. But in 2017, for example, Google DeepMind introduced AlphaZero, which was a program that used reinforcement learning to teach itself to learn without input other than the rules and so on, to play some games. And in 24 hours, it reached a level beyond what humans can usually achieve in chess, shogi, and Go. Okay. There is a reference there if you're interested. And this quickly mastered, for example, the previous version of AlphaGo that we saw from 2016. Suddenly, reinforcement learning, which had been something that had been around in artificial intelligence for a long time, but was quite difficult to use, was much more readily available. Going to skip around this. You have the video if you want more details. Transfer learning is another one of these characteristics of AI networks that became much easier to use and much more effective with deep learning. In transfer learning to use, you try to use the knowledge gained from solving one problem to solve a similar problem, okay? And that's difficult to define, and be advised and be aware that many times if we try to apply our intuitions to what, for example, what a similar problem is, that might not work in deep learning, okay? But let's say that if I have a problem that's similar enough to the problem that I want to solve now, then probably I can reuse the deep learning network that I solved before, that I used before to solve my problem before, to solve my new problem too. And that means that I can adapt the parameters of the deep learning network that I had from solving a previous problem, a problem which was similar enough and that probably I had enough data to solve, to now solve my new problem with fewer data. So I can like sort of use a similar problem as a stepping stone to need fewer data to solve my new problem. Okay, so in deep learning, that means taking advantage of a pre-trained model to speed up the training of a new problem. We do deep learning all the time. We can, for example, I'm again not going to take the time, but you have this on the video. We can recite poetry, for example, in Catalan, and then if we recite poetry in English or Japanese, a part of the recitation is the same. The pitch, getting the rhythm right, that will probably work similarly in different languages. Of course, for each particular language, the pronunciation is different, the cadence is different. So for every new reciting in this language that I want to do, I can use something that from what I already know from learning to do that in another language, but I have to adapt it. So we use transfer learning all the time. But since deep learning networks can also use it quite effectively. Okay, again, be careful of intuition there. Sometimes it leads us astray, but usually we select a first task which we consider is close enough to our current problem, and there we should have enough data. Then we train a network for that one, and then we try to take those weights, those parameters from that network, and use them as a starting point to train for our new problem. And that is widely used. For example, nowadays, anytime anyone does starts training for an image classification problem, the weights that are included by default in deep learning libraries like PyTorch are the ImageNet weights. The rationale between that is that no matter what you want to classify, if you want to classify images of animals or tree species, there are some things like telling objects apart in the image, finding edges, finding differences in color that will have already been codified in a general image classification problem like the ImageNet one. So using the weights, the parameters for the ImageNet problem will help you to train a network for your own problem. Okay. So we can solve quite a lot of problems, like, for example, kanji detection, kanji classification. We also have done things like try to tell tree species. You have an example. This is another one in a black locust forest, in a pine forest. That we had an invasive species called the black locust. I already showed you the sick and dead tree image classification, and so on and so forth. So these networks are very adaptable, and we are going to be using them to solve each of you one problem that we are going to be using in context in globally to solve different problems these next few weeks. Okay. Of course, knowing what a similar problem is quite challenging, and again, do not rely on your intuition. Okay. I wanted to finish this, let's say, explanation part before I go a little bit deeper into task 1 and 2 for the project by talking about the limitations of of this way of working and of deep learning networks. So let me see. I'm setting up the other presentation here. So I'm sorry, I'm getting lost in my own. Okay, now we are here. Okay, so let me first show you some of the things that we can achieve with deep learning. So, for example, let's go to this one. Okay. So this is part of a paper that we published in 2024, I think, from work from Komo Moritake, who's the DA in this subject, by the way. So we try to compare the performance of deep learning networks with human observers for a difficult image classification problem. Let me see if I get the example. Yeah, here I have that. So we had this kind of mosaic from Zhao Mountain in Yamagata, near here. And we had all of these mosaics and all of these annotations. So all of this is pretty similar to what you have now of supple pine bushes. And we wanted to classify those supple pine bushes into different species. So we manually annotated them and we had them colored, for example, here, so you can see the differences. We could also put bounding boxes around them, but here you have an idea of the distribution that they had. Okay, so we could do, for example, image classification here again, putting a bounding box always of the same size around each bush, and that means that some bushes that are bigger are imaged, let's say, are cut. This one has a part that's outside of its bounding box, and some smaller bushes contain the bush and some other things that are not the bush because the boxes are always the same size. But we solve this as an image classification problem. And that meant telling apart these quite similar types of bushes. And we even had data from June, where everything was green, and from October, where some of the bushes, the evergreen bushes, were still green, and some of the other had changed color. The deciduous ones had changed color or lost some of their leaves. Okay, so we used this to, as I was saying, compare the performance of a few deep learning networks, ResNet, like you guys will be using, but also ComNext, Swing Transformer, and Vision Transformer. These transformer networks are the ones that are generally used to run things like large language models, ChatGPT and the like. And we compare their performances. So we had groups of human experts and the deep learning networks. We saw that the computer vision beginners and the computer vision experts, so that I think was, I don't know, the experts, we were a few experts. I was one, but Moritake was also an expert. We had three experts, different experts. We tried to do this classification and we got it right as a group, something like 50% of the time. Okay, and we were the best group. The forestry beginners or the computer science beginners were lower, and the forestry expert was also quite a lot lower. That was because telling apart this is something called a confusion matrix, and we will explain a little bit more about it later. But basically, you have here the predicted sorry, the predicted class, and here is the corrected class. So the correct results are on the diagonal, and anything outside of the diagonal is a confusion, so an error. Okay, so for example, here is a person that got lower accuracy than what you could get randomly. So if you have 6 possible classes randomly, you should get something like 16%, and this person was unfortunate enough to get less than that. And the best results were, for example, here. This is the best result that anyone got, 55% accuracy, which means that this person was doing quite a lot better than the random classifier would do. But still, the degree of success achieved was pretty low, which 55% of the time. And most of the confusion occurred here between these three classes and these three classes. And those are the evergreen classes and the deciduous classes. So telling apart if something was evergreen or deciduous was pretty easy. So there is little confusion here in for many of the observers, but getting it exactly right, not confusing the very similar classes was very difficult. Deep learning networks were able to get much higher results than that. In this general problem of finding the exact same class, they had the same problem of confusing similar classes, but way less. We got, after data augmentation and so on, to 79% accuracy. So 55%, 15% better than, around 15% better than the best human observers. So deep learning networks can find patterns in data and reproduce the expert opinion with a high degree of accuracy. Okay, so that's what deep learning networks can do and what they are good at. Okay, but deep learning networks, which are being applied in many things and will probably have significant impacts in our lives, have several limitations. Some impacts that might happen, for example, self-driving cars, I think, is something that nowadays is growing quite quickly and has a huge economic potential and can change the ways our cities work and our countries work. So I'm really interested in that one and follow the news about Waymo and Tesla and the Chinese companies about that, because that's one of the areas where artificial intelligence can have a significant impact very, very soon. Okay. You have all heard about ChatGPT and natural language processing. I think there are many things that will happen there too. I'm not a super fan of ChatGPT. I don't think it's that useful. I think it will probably bring about some backlash, because I think people are going to realize that it's really not that useful and it's really not going to be able to deliver in many of the promises that are being made, or the let's say things that are being hinted at. Okay, but still, so advances are being made in the process of human natural language, and that includes also, for example, translations and the capacity to communicate with each other in different languages. And I think that is going to be something that will continue to change. And due to the increased availability of databases and the adaptability of deep learning networks, new applications will keep happening. But that doesn't mean that the thing doesn't have limitations. Okay, let's go for some of the limitations. For example, I want to mention a few very quickly, and then I will go a little bit deeper into one, and that will be the end of it. I'm going to be showing. Okay. I wanted to show you the one pixel attack paper, which is one of my favorite papers when I'm speaking about this type of subject. This is a paper from 2019, so it's not so new, but this paper shows how our intuitions sometimes fail and how the way deep learning networks process data and process images in particular is different from the way we do. These guys use something called GANs, generative adversarial networks. So they looked at what one particular image classification network was doing by using another network to look into the results of the first network, okay? But what they achieved was that the second network was able to modify the input. The problem was image classification with a data set of very small images. That's why the resolution is so shitty. That's called Cipher 10. And first, the initial image classification network got very good results. For example, for this image, it got a it classified all of them correctly, all of the images here. But then what the researchers did was change just one pixel in the images, in each of the images. Okay, that's what this is called a one pixel attack. It was not just any pixel. It was the pixel that the second deep learning network decided would be more annoying for the initial image classification network, and that would lead it to error. Okay, and by just changing one pixel, this image that had initially been correctly classified as being a ship got classified with a 99% confidence as being a car. This picture of a horse, just by changing this network, got classified with 99.9% confidence probability as a frog, and so on and so forth. As humans, changing just one pixel in an image will probably not change that much of our opinion of what the image contains, but for deep learning network, the processing of the data is fundamentally different, and even changing just one, putting this red pixel here changes the result from deer, which is correct, to airplane. Okay, maybe not such confident in the airplane, but that was the class that had the higher probability. Okay, so deep learning networks process data in a way that's fundamentally different that we do. Okay, and they have many other limitations too. Let me go to the example that I had before. Sorry, a little bit further back. Okay, so this is an example of what is, I always think, a little bit looking onto the propaganda side of things. This is called an hallucination from a deep learning network, in this case from ChatGPT. Okay, hallucinations are these moments in which deep learning application can output false results because it has gotten confused, or it has decided, or it has detected as correct some patterns that are not correct. ChatGPT is just, and all of these large language models just deal with text. And they glean patterns from the text, and those patterns are exclusively grammar-based. So they can produce sentences that look nice and that look correct and that always look quite similar, if you ask me, but they have no built-in evaluation for what is true or what is not true, what is reasonable or what is not reasonable, what is related and what is not related. They have no significant way to process contextual clues. Okay, they have something called context tokens, but that's not the same thing. And because of that, sometimes these engines to predict text end up predicting sentences that make no sense at all. And they can dig themselves quite deep into some holes, for example. So I started asking ChatGPT about 1 year back about how to ask for the post office. And I did that in order to see what type of indications it did in different languages. And I started with English, and that got a nice result. I then moved on to asking ChatGPT how to ask for the post office in Tokyo, and then it gave me some not great, but still, let's say, not noticeably terrible directions in Japanese. But then I decided to ask about how to ask for the post office in the city of Ulldecona. Ulldecona is a Catalan town, which I have been to in several occasions. And I was surprised that the answer came in French. Okay. So the language spoken by the, according to ChatGPT, very friendly locals in Ulldecona was French. Then I got a little bit surprised by that, and I thought, I don't think people usually speak French in Ulldecona, but I haven't been there so many times. So let's ask about my own hometown in Banyoles. And then I got the exact same answer. in French. And I asked ChatGPT, do people speak French in Banyoles? And yes, apparently Catalan is a primary language in Banyoles, but French has had a significant influence due to the region's historical ties to France. I was a little bit surprised about that. The city is quite close to the French border, something like 40 kilometers. And I was not aware of most people there speaking French on the street every day. So the explanation continued about the Comtat Venaissin, which in the Middle Ages was the apparent reason for this huge influence of France in Banyoles. Okay, and then I was fascinated by that and asked ChatGPT for more information on that. And then I got all of these details about Banyoles being part of the Comtat Venaissin from the 13th to the 18th century. Okay, and that Comtat Venaissin included the Papal States located in southeastern France, which is true, but happens to be quite far from Banyoles, which is on the other side of the border. So I decided to ask for some references, and I even got references to back up all of that shit that ChatGPT was outputting. And the references were either completely unrelated to what was being said. So the Comtat Venezian is something that actually existed, but has nothing to do with Catalonia at all. It was basically on the other side of France. And some general references to the history of Catalonia and so on. And when I asked for references, ChatGPT started outputting some contradictory text saying that, well, maybe the whole thing about French being spoken there is not true. My point here is that while the whole grammar of the whole thing was correct, if we wanted to get something that was useful for anything or that was true, that we didn't get anything on that front. We got lots of consistent grammar. The meanings were more or less consistent with each other and were completely and utterly untrue. They were based in nothing, and that's a limitation that ChatGPT will always have, and that all large language models will always have, because truth is not part of their programming. They cannot know, they cannot output something that will always be true. They never know, they never will know. Okay? Similarly, because there are many, many contextual things like being close to the border doesn't mean being close to any part of the border, but you have to be close to the part of the border that's closer to you, or then it doesn't mean anything. So a county in France being at the border, but at the other side of the border, the side that's closer to Italy, will have no effect on Catalonia, for example. But that's context, and ChatGPT and large language models just cannot do that. Deep learning networks can do many things, can reproduce many minute patterns, but they can never go beyond their programming. And these kind of things happen all the time. Okay? Deep learning is not unlimited. It's not a magic bullet to solve anything. And it's not without risks. Okay? The risks are not killer robots coming and taking our place anytime soon, because that's not the type of intelligence that we are developing. We are not really developing intelligence. We are developing algorithms that can reproduce the patterns that we feed them, and they can reproduce them in a more or less general way. That's not what we usually consider to be intelligence. I think being able to create new things is more close to what we consider intelligent, to adapt to new situations. And deep learning networks today cannot do that. And because of the way they are built, they will not be able to do that anytime soon, probably anytime at all. Okay? But there are risks to artificial intelligence. And I will not be speaking about them a lot, but they do add a certain capacity to process data fast, and that has to be used responsibly, or we risk increasing the effects of some of the biases in our societies. They need to be monitored for things like is all the data used by companies like OpenAI to train ChatGPT and this kind of networks? Is that data that they should be using? Does it belong to them? Does it contain biases that we do not want to spread? Does it contain misinformation? Okay, so there are quite a lot of risks. AI is going to have a significant impact in the job market too. Okay, so we need to adapt. Having ChatGPT nowadays in university classrooms has some very interesting and very good consequences, but it also has quite a lot of annoying side effects when people decide to just not do their homework and they have a new and exciting way to copy it from, even though, for example, in programming courses, the result is usually rubbish. Okay. Okay, so that was a little bit about deep learning in general and so on. I will speak quite a lot more next week about training data and testing data. But today, let's just finish by speaking a little bit more about data and how to use it. And so I'm going back to task number 1 in our programming project. Okay. So as I said before, we are going to be using PyTorch datasets from next week to give our data to the deep learning networks to solve all of these image classification, semantic segmentation, object detection, regression problems that we can solve in a pretty standard way with deep learning networks, okay? So the first thing that we need to do is know our data and prepare it in a way that's meaningful. So for example, we have this kind of label images, okay? And what we want to do in this first task is to move from this, let's say, data that's organized in a way that's more difficult for us to communicate with the deep learning network to one way, which is easier. So in this first task, okay, we have the following steps. So the goal is to have data, and I'm going to call them targets. So the correct answer for each data piece. Okay, so for the image classification problem, what I want to have is a set of images, and for each image, I want to have the correct answer associated to that, okay? So first I need to build the images. What I need to do is cut one small patch around each tree, okay? So that's what I want to do. The coordinates of the tree are in the treetops image, in the treetops binary mask, okay? And we have a function called list from binary that you have here that receives one of these binary masks with treetops and outputs the coordinates of the file. Okay, so sorry, I'm getting lost here. Here, okay? So let's make this a little bit bigger. Okay. So the name of the function is list from binary. So what do I want to do to know? I need to cut patches, and I need to know where they are and what species they are from. Okay, so let me just put this something like here. So first I'm going to go over the treetops file and find the coordinates of all the trees. Then I'm going to be able to cut a patch around each treetop. And I have a function called get create patch for that, okay? With that, I will have my patch, one patch for every tree, okay? And then I also need to know what species that belongs to. Look up the tree species from the label image, okay? That gives me a category, cat. Number one, go to the treetops image and get the list of coordinates, the centers of all the trees. Number two, cut a patch, of course, from the mosaic, from the RGB mosaic, around each treetop, around each of the coordinates that I get from here. So I get one set of coordinates, go to the mosaic, go to the proper place and cut a patch with the create patch function. Okay. So after this, I have the image. And now I want to know the tree species. So I go to the same place, but in the label image and look up what species my patch belongs to, okay? I'm going to call im to the image. And then what I want to do is save im to file, make a folder. Well, I recommend that you make one folder where you store all your patches with a name that includes cat. Okay, so for example, maybe I want to do something like patch number 137, something like this, species 2.jpg or .png, okay? If I make patch names like this, okay, I will always have the species for every patch. Okay, so I need to use the binary mask for the coordinate files, so for the treetops, sorry, to get the coordinates, the mosaic to using those coordinates cut a patch and get the image, and then the label image to get the category of each patch. Once I have this, I will have a list of images in my folder, in my output folder, sorry, as a series of images saved in my output format, and each of them will have a name that will include the species it belongs to. Okay. Then, when I go to the PyTorch dataset, I will need to, and you have all of the definitions of the dataset here, how to handle custom data, and do read this notebook with detail, okay? Because it will be very helpful for you how to use the dataset class and the different parts of the dataset class and so on, okay? So read this Unit 4 notebook in the computer vision course. because you will get lots and lots and lots of information about it. And if you follow the same convention of using something patch and then the species, then you can even basically use the same data set for your code. So in task number 1, you will have to prepare things so then they can be read by a data set, okay? If you use the same way of reading in this part, you're getting the name of the image and the regular expression to get the specific class from the image. So if you follow the same convention, the same way of storing things, by the way, are cut from patches in this other notebook. So if you follow the same way of doing things, you can pretty much mimic this. And if you follow the same naming conventions, you will be able to use the dataset almost as it is. Okay, you do not need to change it a lot, but you can change it just a little bit. In any case, once you have these sets of images with the proper name, what you need to do is build a dataset. First, it will have an init method, and the init method will do something similar to what is being doing here. Basically, walk the data folder, see what images exist in the data folder. And then for that data folder, it will read the different images and read from each image name the proper class, and then output basically a list of images and classes. Okay, it will make two lists. One is called image list, and one is label list. Okay, so this class will have a list of images and a list of labels. So first we will read the proper image, we will add it to the list, and then we will also read the proper label and add it to the list. Okay. Here you have the move axis thing, for example. Okay. I recommend that you leave this as it is. Okay. Because the way tensors are stored inside of deep learning networks and the way OpenCV reads images is not exactly the same. So, and surprisingly, things are read slightly different. So you will need this move axis here. Okay. Basically, if you store your images following this type of naming convention or something similar, then you will be able to reuse this as it is. Basically, what it's doing, it's reading the correct image for every file, and then adding it to a list and putting the label in the same position in the list of labels. Okay, you have more details here. Then the get item method, just when I am told to give an item with one particular index in one particular position, I just have to go and look at the image list and at the label list and output that. Okay. Okay. In this case, because I'm doing classification, I'm going to be outputting a list of probabilities, and I'm going to put zeros in. So I'm not going to just give the target as a number, but I'm going to be giving it as a vector in this case, for example. That's an easy way to work with this type of probabilities. My vector will have 0 probability for any class that's not the label and 1 probability for any class that's a label. Again, you can use this as it is, okay? And so on and so forth. And then the data set gets added some different things and so on. But you can use this pretty much as it is, okay? Okay, I still have a few minutes. So how would this change if instead of image classification, I was doing, for example, semantic segmentation, okay? So in this case, I would like to have my targets would be semantic segmentation mask, okay? Semantic segmentation mask. So how to build images? We have to cut tiles that from the whole of the mosaic. Okay, so we would need to go to our mosaic, start in this corner and define tiles of one particular size, for example, 1000 times 1000, and cut a square here, and then move it a little bit, slide a window. So you will need a sliding window algorithm, okay? And then going on and on and on and on and cutting tiles around here, okay? So here you probably want to do some sliding window code. I will give some references to that later, okay? For each tile, get semantic segmentation mask, okay? So we have to go to the label image and cut exactly the same tile and cut that tile from the label image. For example, here have them the label image superimposed over the mosaic, but here the label image is completely black. Okay, so probably that tile will be pretty not very useful. Okay, and basically I have to save them. Save the tile and mask to file. Okay. So I will get something like tile something 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 dot JPEG and something like mask the same something 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 dot here in this case this is not going to be an RGB image, this is going to be either a PNG or maybe a TIFF. Okay, let's say PNG or TIFF, because here in each pixel you will have one integer value. So you want to build the part of the, you don't want to use a JPEG which has compression. Maybe actually the best thing is to just go with PNG for everything and it will be fine. Okay, so you cut one tile from the mosaic and from the label image, and then you store those two as tiles. Sorry, tiles and masks. And then when you go to the data set, you will first need to build a list of the images that you have and list of the masks that you have. Here, the target will be for each image, an image of the same size with the codes for each class at every pixel. And the get item will be just outputting the correct position in the index. Okay, you will want to also do this move axis thing for the RGB image. You don't need to touch the label image. Okay. Okay. So that's some indications on how to do the first task for image classification, for semantic segmentation. What if I wanted to do, sorry, this was 2. What if I wanted to do, and very quickly because I don't have a lot of time, regression, for example. I'm not going to go to object detection because it's more or less already explained. Okay. In this case, the targets are going to be numbers, amount of, let me call them red pixels, of the desired color. Okay, so how do we build the images in this case? In this case, our images will be well, if we were building from a mosaic, they would be tiles, okay? If you are, for example, simulating them from a data set, you can simulate these tiles using some code, okay? So you can just generate the images as they go. Then you have to save, you have to count the number of red pixels. And that will be the target. Okay. And then save the image with a name that includes the number of pixels. Okay, probably PNG format in this case. Then with the data set, what you're going to want to do is probably, again, read the images, read the information about how many patches are there. And here you might want to consider grouping the patches into classes. If you want to use deep learning network for image classification, then you can just walk through all images in the init dataset, make a note of the maximum and minimum values of red pixels, and then use that to decide on a class. And then, having done that, probably make a list of labels and then do, let's say, low, medium, and high content of red pixels. If you want to do regression, then you only have to read the information of the number of red pixels. Image classification will be easier because you will be able to use the ResNet network already as it is in task 2 and so on, and that will be an initial step to being able to do regression, where you will have to do some low-level modification of networks. Okay. Okay. So today we saw quite a lot of history and general discussion about what deep learning networks can and cannot do. And then we went quite a lot deep, quite deep into task number 1. Okay, please try to solve task number 1 for next week if possible. Okay, try to send me your feedback, ask any questions that you have. And then next week, we will be speaking about task number 2 and the data sets and some of the finer details of how to use them. I will be doing a deep dive into this number 4 notebook and number 3 notebook. The following week, on the 14th, there will be no, let's say, class like this at 8:50 on the Monday because I will be traveling at that time. So I will leave some pre-prepared material beforehand. If I have some time, I want to speak a little bit about training networks next week. So probably in 2 weeks' time, you will have hopefully, let's say, refreshment unit about going into more detail into something that I will have already explained a little bit next week. Okay. For now, this is all. Thank you very much for listening. And please try to start solving these tasks and give me your feedback. Okay. Thanks, everyone.